I'm gonna write up here. Oh, you got that? Yeah, I know. He's like written his own textbook. He's a high achiever. All right, so it's got some extra space right here on this one. Yours does not have this extra space, but I just want to review a little bit here. So we have talked about this a little bit before. If we have a position graph, then that means time is going to be on our x-axis and position, or sometimes it might be called distance, will be on that y-axis. So like let's say our time was in seconds and our position was in meters. Okay? All right, so I've got some sort of function here. If I take the derivative of this, so let's call this S of t. They use the letter S for that. Sometimes they use an X or Y. It just depends. So my position function is S of t. If I do S prime of t, which would be the slope of the tangent line, right? What is that going to give me, and what units would I use to measure it? It'll give me slope, which is going to be my velocity, because it is my change in y over my change in x, which is my slope, right? What am I measuring my y-axis in? Meters. What am I measuring my x-axis in? Seconds. So velocity in meters per second here, right? So we take our y-axis units and divide by our x-axis units. So what if we took our velocity function, so this is still time, and this is going to be velocity, okay? So this is meters per second, and then time, so we've got some function. I could actually think about what it's going to look like. So what about if we take the derivative of this? So we're talking about S double prime of t, or we could call it V prime of t, the derivative of velocity. It is the rate of change of your velocity, which is going to be acceleration. Okay, so this is going to be acceleration. Yeah. Okay, and so if we think about taking the derivative, it's the slope of the velocity graph, right? So it's change in y over change in x of our velocity graph. How do we measure our y? Meters per second. Per second. Okay? So I usually just tell students to say meters per second per second. Okay? But you also could do this, meters per second divided by seconds. That's like seconds over 1. So that's meters per second times 1 over seconds. So you could do meters per second squared. I usually don't tell students to do that, mostly because they put the square in the wrong place. They do meters squared over seconds, which is not correct. It would not. So. Yeah, square meters per second, that'd like be the area changing per second. Yeah. Yeah, it would really be wrong. Yes. You would have the rate of change of the acceleration. So it would tell you whether more or less whether the acceleration is accelerating. Yeah, we won't go that far most of the time. Okay, so all right. Okay, so he has these nice little charts here. S of t is the position. V of t is the first derivative of s, which is the velocity. We've worked with that a little bit already. And then if we take the second derivative, then that's going to be our acceleration function. Okay, so notation for this, you might just see y primes or f primes. When we get past 3 little tick marks, they just start putting parentheses 4, parentheses 7, parentheses n, however many times you're taking the derivative here. We don't do third derivatives, fourth derivatives, fifth derivatives often, but you may see them some. Typically, if you see them, they're going to be on problems that are easy to take derivatives of.
I found Mr. Records. This is him. Is this him?
Yeah, I think so.
Why is he at a KKK meeting?
I don't think it's Mr. Record in that KKK meeting. There's probably more than one Mr. Record, hopefully.
So it was the
Hopefully.
This is not a nice picture to pull up my first image on.
It just says, I have found Mr. Record.
Yeah.
Oh my God.
So, Daniel, you're... Okay. All right, so, for second derivatives with the dy dx notation, it's kind of strange here, the dy dx. So if you think of, he's written it over here, you're taking the derivative. I don't usually write it like he's written it. I write it like this usually. I usually do, like, we use this notation often that means to take a derivative. So if we take the derivative of dy over dx, there's 2 d's here, so that's d squared y. And then on the bottom, it's like dx squared, although they don't use the parentheses there, so d squared y over dx squared. It's not terribly important. Usually it's going to be written in the problem somewhere, so just copy the way it's written there. You know, they're not going to try to trick you up by putting the squares in the wrong spot or something. Yeah, this right here means take the derivative of whatever's in the brackets with respect to x. dy over dx means you have already taken the derivative of y with respect to x. But let's not get too caught up. Just if you see this right here, it means second derivative. You're probably not going to see third, fourth, or fifth derivative. Okay. All right, so if we're looking for a second derivative, you just got to take the derivative twice. So f prime of x here is going to be 6x squared plus sine x, because the derivative of cosine x is negative sine x. And so those two negatives make that positive. What's the derivative of natural log? And what's the derivative of e to the x? E to the x. Okay, so that's our first derivative. To take our second derivative, we just have 12x plus cosine x. I love this problem because it makes you remember how to take the derivative of all of these basic types of problems in one. Derivative of sine is positive cosine. Not natural log. So this, remember, 1 over x is x to the negative 1 power. So it's going to be negative x to the negative 2 power. Yeah. And then that e to the derivative of e to the x is still e to the x. Correct. Yeah. Those two are not. Yeah. Right. You're technically kind of always doing a chain rule, but the derivative of an x is just a 1, so it doesn't change anything. And the natural log and the e are anything separated out by plus or minus signs, you're taking the derivative of them separately. You don't have to do product rules or quotient rules or anything like that.
You do keep the negative if there was like a negative in the x out in front, right? Like for the negative in the x. Just keep it out in front.
Yeah, you would just multiply it out front, yeah.
What if the product rule with 6x squared, is that frowned upon?
That very much overcomplicates it. So yes, it would be frowned upon.
Does it give you the same thing?
It would, because you would do 6 times the derivative of x squared, which is 2x, plus 6x, or I'm sorry, x squared times plus x squared times the derivative of 6, which is 0. So that would go away and you get 12x. But please do not do that.
That's awesome.
But it does work. Yeah.
But it didn't work.
You do tend to overcomplicate things.
It did work.
Okay. All right, questions? So a lot of this is pretty straightforward. You're just taking the derivative more than once. There's not anything so special for me to teach you about it because you already know how to take the derivative. You just got to do it twice. So, all right. Okay. So, how do you pronounce that? Burj Khalifa. Khalifa. Yeah. All right. So, anyway, tallest building in the world in Dubai. All right. So, okay. All right. Let's focus back on this problem and not Rishi's love interests. Okay. All right. So this is the tallest building in the world. And so they give us this position function, which should look kind of familiar if you think way, way, way back to pumpkin chunking and catapults and stuff in Math 1.
As soon as I saw the negative 60.
Yeah. So this particular ball has been thrown from the top of this building. Obviously, it has some negative velocity to begin with, so instead of just dropping it, they threw it. We are ignoring air resistance, yes, because that will make it more complicated than we're willing to or able to handle. So, if I want to know the velocity of the ball at t equals 5, what do I have to do to find the velocity? What do you think, Ethan? Derivative. So, we're going to take the derivative, which will be negative 32t minus 10, and then at 5, oh, yes, thank you. What I really should do here, I should not have a prime right there, but what I really should do is I should say s prime of t equals v of t. So I am showing that I know the derivative of s is the velocity. There, I should not have a prime right there on my v. So this is not velocity, this is height.
So you're just saying that s prime of t is equal to v of t?
Yes.
But that's the velocity equation.
This is not a velocity equation. This is the velocity equation.
Wait, so then what?
This gives us the height in feet the ball is from the ground
So what if you
at a
don't say
specific
that?
time. Ideally, you were going to put S prime of t equals V of t. That's the best thing to do.
Oh, so the derivative of that is going to be the equation.
Right.
We're not.
And so our velocity at 5 is going to be negative 170 units. Not meters. Feet per second. Not squared, because squared would be acceleration. Alright, if we want to find the acceleration in part B, what do we have to do? Derivative of the velocity. So I could call it S double prime of t, or I could call it F V prime of t. So I could say either one of those. You don't have to put both. And that equals A of t, which is going to be just negative 32. And so it doesn't even matter what you plug in, but if you do plug in 5, it's still negative 32 feet per second, which is your acceleration due to gravity on Earth. So it is going to be the same everywhere on Earth. Yeah, it's 9.8 if it's meters.
So this is the part of the pumpkin function that you said that we couldn't do until we got the calculus.
Yeah. It is not a velocity, it's your acceleration. So, acceleration due to gravity is always the same. So it doesn't matter whether, like, I take this protractor and drop it, or whether you climb to the top of the school and throw Daniel off. Terminal velocity involves air resistance. So in this case, we're ignoring air resistance, so it is not, like, that would be a different calculation. Because terminal velocity would be different for different, like, things that you were dropping. It would have to do with when your air resistance and your acceleration, or your acceleration kind of like even out, I guess. So it can no longer accelerate because of air resistance. Yes, forever. If there is no air resistance or it doesn't hit the ground. Yeah. Right. So this would have to be like in a vacuum. Yeah. Yeah. It's if we had like some sort of vacuum tube that was. Well. It would, and we'll see that on the next problem. So it's going to be different. Okay? When will the ball hit the ground? Okay? Why S of t? It's a height. So we want to know when its height is 0, right? So we'd have 0 equals negative 16t squared minus 10t plus 2717. You're not going to do that. I don't think this will, I'm pretty sure this won't factor. I worked it out earlier. So what else do we know how to do to solve this? Quadratic formula, 10 squared plus or minus square root 10 squared minus 4. All right, so Alright.
Yeah, but I don't try to.
Alright, and
It's not going to be possible.
alright, so this is something you're gonna have to have a calculator for. You should get 12.722. You also get a negative answer, but that is not valid for this particular situation.
Calculators or not?
I believe. Oh, look how together Mr. Record is. Look at the calculator symbol he's already got up here next to this example.
You don't even know how to use ours.
So if we had paid attention to that, which I already knew because I worked this out myself, that you had to have the calculator for it. But okay. All right. So whenever it hits the ground, we want to know what the velocity is. This is something you want to know because let's say you are standing at the bottom of this tower and somebody throws the ball off and it hits you in the head. When it gets to the zero, it will eventually be zero, yes. But we want to know at the instant when it hits the ground what the velocity is. Or if you're standing underneath this thing, at the instant when it hits you in the head, how fast is it going? And is it going to kill you or not? I don't know. We're ignoring air resistance because it makes this problem too hard. Alright, so we need the velocity formula. We're going to plug 12.722 seconds in. So negative 32 times 12.722 minus 10. And I already did this earlier. It's negative 417.119 feet per second. It's feet.
It's essentially moving more than 4 football fields every second.
Yeah.
Wait, not feet per second?
No, it's moving.
It's a little more than a football field per second.
Moving just over a football field.
Yeah.
Just
I thought it was meters.
Just over a
Why is
football
it
field.
feet?
Exactly.
Yeah. So the size of the object will not affect its speed. So like it could be a bowling ball or a bouncy ball. It's going to have or a piano. It's going to have the same speed. But it would affect the amount of air resistance would be affected and the force it would hit you with.
The inertia.
Piano would be worse than bouncy ball. Although at this speed, bouncy ball could possibly kill you. I don't know. I don't want to try.
I concur.
Yeah. All right. So.
Let's just huddle up in a circle and check it.
Okay. All right. Okay. We just got a couple more here. All right. Let's skip that one. We're going to do 4. Gravity is different on the moon. We're not going to do that one right now, though. Let's skip to the 4th one because we're about out of time. All right. Okay. Second derivative of cosecant t. All right. Turn around. All right. First derivative. What is the derivative of cosecant of t?
Negative mu derivative.
Over square root 1 minus.
This is not inverse cosecant.
Oh. It's okay. Then that's just cosecant cotangent.
Cosecant t, cotangent t. You should know it. Daniel is impressing me with his memorization skills there. Alright, so we got to now take the second derivative of this. What are we going to have to use to take the second derivative? Got to use that product rule here. Okay? So it's going to be negative cosecant t times the derivative of cotangent, negative cosecant squared t, plus cotangent t times the derivative of negative cosecant, which is cos.
We literally just did it. We just did it.
Okay. All right. So if I combine these, I'm going to have cosecant squared t. No, not squared. Cubed. You should have a negative times a negative there, which is going to give you a positive. And then we'll have plus cosecant t cotangent squared t. Now, something to remember is that we know our Pythagorean identity. You guys probably remember this one really well. Sine squared theta plus cosine squared theta equals 1. All right, we remember that one. There is one for cosecant and cotangent. Okay, so if I divide everything by sine squared theta here, one plus cotangent squared theta equals cosecant squared theta. So, because this I've factored out here as a cosecant, I'd really rather turn everything into cosecants than cotangent. So, I'm going to subtract my 1 here. So, cotangent squared theta equals cosecant squared theta minus 1. So I could write this as cosecant t cosecant squared t plus cosecant squared theta minus 1. So this could be cosecant t 2 cosecant squared t minus 1. No. Cosecant t times 2 cosecant squared t minus 1.
Is there, does it say this to be a t on the second last line?
Yes, it is. Yes. We did. This is our second group. We did this stuff in pre-calculus, but I figured that you probably forgot it. Trig identities.
Remember what I told you that other week in the time about trig identities?
Yeah. And so they might distribute that cosecant back or something, but it'll probably look something like this. And if it is free response, don't simplify any further. Okay, so